All right, so let's do section 3.3. So this is graphs of quadratic functions. Quadratic functions are kind of one of the most well-behaved types of functions. It's not quite as easy as linear, not quite as well-behaved as linear. Linear is maybe the simplest one that's still interesting. This one is slightly more complicated and also slightly more interesting. So we get to do few different things with these. They come up fairly often. It's not at all uncommon for something in physics to be represented by an x squared or some transformation of y equals x squared. So you should be familiar already with the fact that that your basic parabola has some symmetry, and we worked pretty hard on 2.5. If you haven't already watched that video, you should definitely watch it now before you watch this one. With transformations are something you can do with any old graph that you already have a picture of that you understand. But in particular, it's like once you have y equals x squared and you have some transformations, it turns out that that kind of tells you everything that there is to know about y equals x squared. So we'll explore that a little bit more. The reason why y equals x squared is kind of that in transformations put together. The reason why that tells you everything is because we have this thing called completing the square. And if you complete the square, that process, what do you end up with? Well, you end up with a transformation of the basic quadratic. So kind of like basic quadratic is sort of, or maybe fundamental. Okay, so sure, this is our old buddy y is equal to x squared. It's a good one. It's just, sure, we know if we go out to plus or minus 3, then y goes all the way up to plus or minus 9, but at some point in your life, you should also maybe try a few other ones in your calculator. Like if you plug in 1/2, you end up getting 1/4. But so you know that if you plug in enough points, you should sort of get a feel for how this is actually kind of smooth. It's hard to draw it perfectly by hand. Like it's not quite as, it does start bending kind of right away. It starts out flat, but it starts bending somewhat quickly, and while it curves up, it hits these points, and let's see, that's call that the y-axis, call that the x-axis. Okay, well, so what's really cool about transformations is that actually this case is just about as general as it gets for polynomials. Because if you expand this out, well, what do you get? Well, you could expand this out if you wanted to, but let's look at a picture of this first. So what's going to happen? So if if it's x plus h, then you move it by that amount to the left, but it's kind of customary to write it with a minus here because what did we learn when we did transformations? We did this. So we had x plus or minus a constant. So we had a plus here, and what is it? So move left by negative h, which means we move to the right by positive h. Okay, so let's take and then we stretch vertically by a, and then we add a k. So we shift it left by negative h, which is like a double negative. So basically move to the right by h. That's why we like to think of it as a minus, and then we add k. So okay. Start with the original. 1, 2, 3, 4. Well, I'm not going to make it that far, but let's do just for starters. All right, let's just start with a is equal to 1, but let's do y equals x plus this, and then I don't know. So if we have x plus something, we move it, we start with the original, y is equal to x squared. So this isn't the final picture, this is good old y is equal to x squared, but we move to the left by -2. We move to the left by -2, then that means we're moving to the right by +2. And we move up by 1. So we're actually maybe a new color for that. Let's do a new color. So I put a plus here because it's left by -2, which is the same as right by +2. So we move right by 2 and we move up by 1. And I have no a term, so this time I didn't stretch it, but if I were to stretch it, it would be stretched from this new point here. So it would be, but anyways, so this time a was just 1, but we had 2 shifts. We had a horizontal and a vertical shift. So 1, 2. We end up here, up here. My scale got a little bit stretched out, but it's basically like this. Okay. So y is x minus 2 squared plus 1. Looks like that. And so this is kind of looks like that. I just want to emphasize something here, and just what happens in general. So moving to the left by -h is the same thing as moving to the right by +h, so it's like a double negative. So basically, if you write it, if you think of this as your standard form, then this thing is called the vertex. In this case, h was, here it is in standard form. From the point of view of transformations, the standard form was you had x plus however much you shift to the left. But when we want to sort of have the simplest representation, we write it down this way as x minus h squared times a plus k, then it's in this standard form. And there's a vertex, so it's h and k, which is, in this case, it's 2, 1. All right, so what else can we say? That's good to get us started. Let's just keep a running summary of all the stuff here. Um, yeah, so maybe I'll get rid of that. Okay, so I think I wrote some of this on the other side in advance as part of a summary. Yeah, anyways, that's fine. So remember what we said about transformations previously. If a is positive, then it's either you stretch it if a is bigger than 1 and it's multiplying by like a half or a third would shrink it, but it's still going in the same direction. So the shape is called a parabola. That just means, well, if you take the function, you shift it right or left, but then you also multiply the x squared function by a constant. And if it's positive, then it's still going. It's the original parabola. It's been sort of stretched or shrunk, but it's still facing the same direction. And it's hard to draw perfectly symmetric. I'm trying not to block the camera with my body, but it gives me a weird perspective. I can't quite see what I'm doing. Now, that's closer to symmetric. And if I just draw the arrow in exactly the same place, it looks closer to being perfect here. Now, there it goes. So there's the mesh point HK, which is called the vertex. Regardless, there's always a vertex, whether A is positive or negative. The vertex is always at HK. And just remember that the axis of symmetry is, technically speaking, it's not just a number, but it's the equation x is equal to h. So x equals h. Well, here's y can be anything, but h, this is just a line of symmetry. So where's this line of symmetry, where everything on that line is the right side is equal distance on the left side to the other one. So these 2 points are in the parabola, but they're equally spaced from the line y is equal to x. Or sorry, x is equal to h. Sorry, x is equal to h is this line. And that's the same thing as the x is equal to 0 axis of symmetry for the basic parabola. Well, if you move the entire picture to the right by h, then the axis of symmetry is sort of all the points that are symmetric to that original line are symmetric in exactly the same way to that translated copy of the axis. So if you move this up and down, left, right, symmetry is like a property that sort of carries over exactly in that way. So you just sort of visualize it, and that's what it looks like. So what I want to say about the vertex is, if A is bigger than 0, then there's some things that are specific to that. So one is that the parabola still opens upward. and the vertex is a minimum, or it's the absolute minimum, that the smallest that the function ever gets, but it's also a relative minimum in the sense that it's smaller than all of its nearby neighbors, but it's also smaller than everybody else on the entire real line. So so nearby, I'm lower down than I am everybody else. But also, just no matter where you go, the function's never going to go below that. And so if A is less than 0, there's still a vertex, there's still an axis of symmetry. We've still got this HK. Well, what do we do? If we have y equals minus x squared, and then we shift it left, right, up, down, we still have this point, but it opens downward. So that's changed. It opens downward instead of upwards. And then what do we say about the vertex? The vertex so one of the classic applications of this is acceleration due to gravity. You throw a rock upwards into the air, it goes up for a bit, it slows down, and then it falls. It reaches a maximum. So A being negative means that gravity accelerates it downward, even if it's initially going upward, and then it goes as high as it's ever going to go, and then it comes back down. All right, so that's kind of a summary. We sort of so that's a good thing to look. This is a good time to pause it to collect some basic information. I want to say a little bit more, and then I want to do some problems. Let's see. All right, so so maybe let's do some of the simpler problems. If it's already in this form, then everything's really, really nice. If it's in this form, a lot of things that you really want to know are already given to you. Try this a little bit more. Okay. I can call it f of x, so whatever function it is. right, so let's do that one. So for A, it's not quite in standard form, it's almost standard form. F of x is negative 2x plus 1 squared minus 1, which is it's x minus negative 1. So h is not 1, because that's not quite the hk form of the parabola. This is hk form. It's a x minus h squared. And if I want to be super duper, yeah, so it's supposed to be plus k at the end, so h is negative 1. And then k is also equal to negative 1. So I mean, if it looks like this and you just tell me h is minus 1 and k is negative 1, that's not too big of a leap. It's the ones that are not in HK form already. If they haven't already completed the square, then you have to do a little bit of work. But if it's already in this form, you can, once you get comfortable, you can just look at it and yeah, h is negative 1 and k is negative 1. And make sure this, if I'm putting this on the homework, I'm going to ask a quick why question. It's not too complicated. It's just a is positive or a is negative, or so. And let's have a part C as well. So give the equation for the axis of symmetry. All right, so is the vertex a max or a min? So the vertex is at minus 1, minus 1. Well, it's because it's a maximum because a is negative, a is less than 0. And parabola, or the parabola, I want to be more proper. And this is kind of an important fact. You see these pretty early with parabolas, but it's actually a very important feature that informs a lot of your future intuition about how do functions behave, and even in calculus, this is an important feature. So, and then for part C, so axis with an x, axis of symmetry, x is equal to minus 1. Okay, so that's sort of it for how that stuff goes. Yeah, I want to see a little bit more than I than. So there are some problems that are like this as well, and let's stick with standard form. Everything's a lot nicer with standard form. So let's keep doing it. So let's yeah. So I'm gonna do something that's it's not too hard. It's slightly harder than what you'll actually have to do, and even then it's not super hard. I just want to give you the right idea. I want to show you. Once you get part of the way there, the rest of this problem is going to be pretty straightforward. So here I have a point at 1, 2. All right, so I kind of want to ignore these other points, but I'm gonna have these. I'm gonna include these other two symmetric points. I don't want the rest of the problem to depend on my art skills. I just want this point 3, 2 to be very clear, and I want this point 5, 0 to be very clear. All right, so yeah, let's just say y is g of x, then say that it tells you given that it's a quadratic. So given that y equals g of x is quadratic, it just means a times x minus h squared plus k. Well, we know immediately that y is equal to x minus, well, h is 3. That's h and that's k, so we know it's this. And well, the only thing is we don't know a yet. So a lot of times what's going to happen is they're just going to give you multiple choice, or you match the graph with the parabola, and then like the vertex might be wrong, and then one of them, a, could be negative instead of positive. So it's going to be wrong for there's h, or there's k. We found k, or in the picture k was 2. But what we know immediately is that a is the basic parabola goes like this. This is the opposite. It's vertically reflected. And maybe this is all you need to know. Your answer, your answer is going to look like this, and you have a negative number for a. And if it's on my lab, or if it's multiple choice, and they want to make it an easier problem, well, first of all, make sure that h is the right thing, make sure k is the right thing, and then out of whatever's left, only one of them is going to have a negative. And if it's multiple choice, you could just plug in a 5 into your equation, and then either it satisfies the equation or it doesn't. But let's pretend it's not multiple choice. How would we do it? Well, our parabola satisfies when x is 5, y is equal to 0. So 0 is equal to, when x is 5, what do we get? We get a times 2 squared plus 2 is equal to 0. So 2 squared is 4. So 4a plus 2 is equal to 0. So 4a is equal to 2. A is, sorry, I subtracted 2 from each side. So 4a is negative 2. Or, divide by 4. A is negative 1/2. So that's the form of a parabola that has vertex 3, 2. We need some point on the parabola that is different from the vertex. We don't learn anything new from the vertex. If we tried to plug that in, we would just learn that 2 is equal to 2, and then there'd be no a term. But if you pick a different point on the parabola, you do learn what a is, because a becomes something that you solve for when you plug in the other x-y pair. So x and y, x and y. So y is 0. So we have h, we have k. Plug in everything. A is the only thing we have left to learn, and then so y, the general equation is we plug in the value of a back into what we know already. And that's something you can always do. If you have a vertex and you have one more point, you can always find an expression like that, and that's pretty nice. Okay, so you might want to pause that. I'm going to take a minute here, and then I'm going to I want to start talking about what if they have not completed the square for you. Sometimes it's not so obvious where the vertex is, but then we can still do it. We've learned a few things, and we're going to learn a shortcut, a sort of faster way of figuring it out. It's still not going to be instantaneous, but we can still do it. All right, so let's keep going here. So I just want to remind you what we just did there. A lot of problems, if it's multiple choice and you've got the h and the k, see if process of elimination, just the fact that you know that whether a is positive or negative, that could very easily be the only remaining bit of information required to solve the problem. So that seems to be how the mind lab test is and how the book problems go. I showed you a little bit more because why not? It's not too hard, and it's kind of a nice thing to know. But this one is it looks simpler, but it really isn't simpler, and for the reasons that we kind of just discussed. That vertex is a very important point that gives us a lot of crucial information. So what I want to do is I want to how do we get the vertex? Well, what we learned is that you can always do it. It's always possible. We didn't have a name for it. We didn't call it the vertex when we did completing the square. But that's our new word for what is the thing that we end up with. So I want to take this and I want to go from here to something that looks like that instead. So I don't want to do all of it. I just want to give you enough to give you the right idea, and then I want to show you what the shortcut is. So the process looks like this. So if I was thinking one step ahead here. The first step is you factor out the a. Well, it's like there's an a over a, you can always have times a divided by a and factor out the one on top. So it's you divide by a and you multiply by a, but that a is something I want to factor out from the entire expression here. And then yeah, same thing with c. So if I keep the c inside the same parentheses, then I have to factor the a out. So I want to do just enough with this to give you an idea of what happens. Okay, so with completing the square, we took the coefficient on the middle term, we took half of that, which is b over 2a, and then we squared that thing, but then we had to add and subtract it. And what's the big super duper important thing? It's this I think I put green parentheses is what I used. So that thing is a perfect square. And what was it? It wasn't x plus b over a, it was x plus b over 2a was the magic thing that you had to get. And then some other stuff, and it was kind of a pain. But what I want to really emphasize here is this. So let me write this so it looks like the real payoff is right here. So I'm going to write this as a double negative because now it looks like x minus h squared. And this a on the outside let's just call this plus capital M, because we're going to learn a shortcut here. What I'm really trying to figure out is h. Let's just find h first, and then I claim that there's a shortcut for finding k. So we've got a times something squared plus something. So it's just, if we distribute, then we've just got a times distributed the a to these two terms. So a times this and we can just take this red thing here, we can just call it k. So we just give it a whatever we end up with. We'll worry about that later. So we have to solve for k eventually, but the big thing that's super duper important is we've written it as a times x minus something squared plus k. So that thing is h. So that just says we do this once just to prove that this magic formula always works, which is kind of a pain in the butt, but once you do it, you know that this is a magic formula, that it always works. If you have it in like the quadratic formula kind of format, ax squared plus bx plus c, then h is this, and then actually there's and then the sort of shortcut that you can take is K is just, I'm calling it P. So just, I think I originally called it P of X. Let's say you don't know what K is, but you have it in, let's say this is the equation that you have. We just solved for H. It's negative B over 2A. Negative B over 2A. But then you solve for H, but then you plug it into that polynomial and you get K. And then A is just A, and you have everything. So that's really cool. And this is what I wrote down on the other side. And we'll do it. We'll do stuff with this. It's pretty straightforward, and it is an alternative way of completing the square. We teach it this kind of long way because you have to do it that way at least once just to know that it always works and you understand why it works. And it's a little bit of a hassle, but once you've proven once and for all that this is always going to work, maybe the crucial fact to memorize is that this is the H that you end up with, and then plugging that into the function. Well, if you plug an H into a parabola in HK form, you know that plugging in an H is going to make this vanish, and then whatever's left over is K, because it's an actual point on the graph is HK. So you plug H into this, you plug H in for X, whatever's left over has to be K, because it's a point on the graph. So that's it. It's almost magic, but let's do it. So proving it was kind of a pain, but let's actually use it. Once we have it, we can just use it, and it's very nice. So let P of X be 2x squared minus 6x plus, I don't know, 7. Sure. All right, let's do that. So and it's in our equation is in ax squared plus bx plus c form. That's something to check really quick, but yeah, it's in that form, which means that the h is negative b over 2a, which is negative 6 all over 2 times a is 2, which is 6 quarters or 3 halves. Let's just write that down separately. Yeah, we just use this expression here. So, K is just the y value on the graph when you get to the magic h value. That is for the vertex. So we plug this in. Well, 6 times 3 halves is just negative 9. All right, so these two right here are just negative 2, but this is 9 halves minus 2. So that's like subtracting 4 halves, so that's positive 5 halves or 2.5, whichever you prefer. and that's it. That's well, that's K. So vertex is okay. That's not it. The final answer is 3 halves, comma 5 halves, or I'm not sure which one of these MyLab prefers, but these are both exact forms of the answer. So maybe MyLab is going to be fine with either, but I'm not. Just try it, and if it doesn't like it, do the other one. That's pretty neat, and in particular, if you wanted to complete the square, okay, there's all the work that we just did to find K, but it's it is a legitimate method of completing the square. It builds on top of work that we already did, but once you know once you do that work once and for all, that's some valuable knowledge that you have that you can apply, and it's maybe easier to remember how to do it. It's a little bit easier to apply. I'll let you do it on the homework if you haven't done it already. I think that one is, yeah, it's going to be due in a couple days, but that is a valid way of completing the square. So because it's the same A, the two different standard forms, the HK form and the AX squared plus BX plus C, those two A's are literally the same A. So what do you need? You need A, you need H, you need K. You find H as negative B over 2A. K is just you plug H into the polynomial. And there you have it. It's very nice. So any question that we could ask about a quadratic, we could ask the same question about this. So if part A is to find the vertex, let's just take the exact same problem. We've already done the hard part. Find the axis of symmetry. Well, it's always just x value. X is equal to h. So the final answer is x is what was h? X h was 3 halves. That's the axis of symmetry. So it would open to upward. So A is positive means that the smiley face, which means there's a minimum at the vertex. So H and K was 3 halves, comma 5 halves. All right, so so here's 3 halves, here's 5 halves, and here's its opening upwards. If you really wanted it to be nicer, then sure, this should go all the way up to something like this. If it's a multiple choice problem, then by far what we've done so far is already enough to identify what we're looking for. It opens up, it has this H and this K. If I run a really, really nice graph, I might specify to use, how many, maybe I'd tell you to use like 2 or 3 points to the right of the vertex, and then use symmetry. So you would have a total of like 5 points, for example. That would give you a nicer picture, but for multiple choice, finding the vertex and the axis of symmetry and which way does it open, up or down, that gives you a pretty good start on those. I guess maybe a word problem. I didn't see any really hard word problems on the test. Some of them are a little bit too fancy and involve other things. But I think the test that I copied from somebody else's course stuck to mostly the more straightforward ones where they just tell you the equation already. Yeah, I think that's it. I think that's about all I wanted to say. If I stumble across something that I missed, I'll just upload another video. But that's the heart of it. It's already a long video, but I think we covered a lot of important stuff. And this is a nice shortcut for completing the square. So you'll definitely this very last example was very, very nice, and you'll want to look at that one again maybe. But that's it.